This video is a solution for problem number 71 in chapter 12, section 1 of Calculus, the Stewart version, the 6th edition. And in this particular section, which is on sequences, we have a Fibonacci sequence question, and we're trying to determine what the sequence is, and then also evaluate the limit of the sequence. So if we look at part A, it says that Fibonacci posed the following problem. Suppose that rabbits live forever and that every month each pair produces a new pair, which becomes productive at age 2 months. If we start with one newborn pair, how many pairs of rabbits will we have in the nth month? So let's go ahead and look at a chart, which would be the easiest way to go about evaluating this, to see if we see some sort of sequence or pattern with our sequence. So we have month number and then the number of rabbits. And then we also have a guide here at the top, because as I said in the problem, once a pair of rabbits reaches 2 months, then they're productive, meaning they can produce another pair of rabbits. So when we have a newborn pair, we're going to use just 2 unfilled circles. So this is our newborns. Then with the pink circles, this means they're in their first month, so they're not yet ready to be productive, but they're pretty close. Because in the next month, they'll be green, which means that they will be productive. And the idea is that they'll continue to be productive while they're here. So they won't just produce another pair of rabbits once, but every single month they'll produce a new pair. So let's go ahead and get started, starting in month 1. So they tell us that we had a newborn pair in month 0 essentially. So once we get to month 1, they're in their first month. So there's our first little set. Then when we go to month 2, this pair that was in their first month is now productive, and they produce a newborn pair. Then we head over to month 3, and in month 3 we still have our initial productive pair. There they are. And this next set, which was a set of newborns in month 2, is now in their first month. But remember, we said that as long as a set of bunnies or rabbits are productive, they will produce another newborn set. So there it is. So this comes from this green set. That's their pair. So when we go to month 4, we find that we still have our original productive set. And now the bunnies that were in their first month, rabbits that were in their first month in month 3 are now productive in month 4. So that means these 2 pairs will produce 2 new pairs of their own. And the set of newborns in month 3 are now in their first month in month 4. Then we get to month 5. And in month 5, our number of productive rabbits goes up 1 more. So we have these 2 pairs, and now this set that was in their first month becomes productive, which means now you're looking at 3 newborn pairs. I'm actually going to put them underneath here because I have a feeling we're going to start running out of space pretty soon. And these 2 newborn pairs in month 4 are now in their first month in month 5. There we are. So now we get to month 6, and I think we're going to stop at month 6 because we're going to start running out of space here. And we find that we had 3 productive sets in month 5 plus the 2 that were in their first month. So now we have 5 pairs of productive rabbits in month 6. And with these 5 pairs of productive rabbits, they'll produce 5 pairs of newborns. So here's 1, here's 2, 3, 4, and we'll bring down the 5th. 5. And we had the newborns from month 5, which will be in their first month in month 6. So here's 1, 2, 3. Excellent. So like I said, we're starting to run out of space here, but we should have enough months charted to figure out what the sequence and pattern is. So let's go ahead and take a look at the number of rabbits we have for each month. So in month 1, we had 2 rabbits. In month 2, we had 4 rabbits. And then in month 3, we had 6 rabbits. At this point, it almost seems like it's just going up by even numbers. So we would go 2, 4, 6, 8, 10, 12. But let's see what actually happens. When we hit month 4, we have 2, 4, 6, 8, 10. So we actually don't have that pattern. So we have 10 now. And then in month 5, let's see what happens there. 2, 4, 6, 8, 10, 12, 14, 16. So we have 16 rabbits here. And then in month 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So now we're up to 26 rabbits in month 6. So we started off in month 1 with just 2, and by month 6 we had 13 times that. We were at 26. So let's see if there's some sort of a pattern with the numbers. Something I'm noticing, and you may have seen the same thing too, is that you have this 26 here and it's preceded by 16 and 10. And if you add those two, you get 26. Perhaps there's something to that. Let's see. So if I look at 16, yeah, if I add 10 and 6, there's my 16. And if I look at 10, hey, there it is again. 4 plus 6 gives us our 10. And with the 6, 2 plus 4 gives us our 6. So we can say that the sequence pattern for this particular set, if we call it f sub n, is really based on the 2 previous months to be able to determine what's happening in the current month, which is totally a legitimate setup for a pattern for a sequence. So we would say in the nth month, if I want to know the number of rabbits I have, I need to look at the previous month, which we'll call n minus 1 because it's 1 month behind. And we'd add to it the month behind that, which we'd say is n minus 2. Okay? So when we looked at month 6, that would act as our n. N minus 1 or 6 minus 1 would give us 5. And n minus 2 or 6 minus 2 would give us 4. So we'd add up these 2 months to get the next month. So to get, for example, month 7, we look at month 6 and add it to month 5. Or month 8, we look at month 6 and add it to month 7, so on and so forth. And in fact, we find that yes, this is the pattern that Fibonacci had in his sequence, and that was in our earlier example in the section. So now that we've proven this part, let's go on to part B. So in part B, it says that we should assume that a sub n is a ratio of f sub n plus 1 divided by f sub n, and that we should show that a sub n minus 1 equals 1 plus 1 divided by a sub n minus 2. It's a lot of words. Let's go ahead and write it out. So we have a sub n is supposed to be f sub n plus 1 divided by f sub n, and they want for us to prove that a sub n minus 1 equals 1 plus 1 over a sub n minus 2. Now, in order to do this proof, we're going to need some information from our last page, and in particular, our definition of f sub n. We said f sub n is equal to looking at the previous month and adding to it the month prior to that. Okay, so we're going to end up using this to help us to prove this section here, prove this equation here. So let's take a look at this a sub n, look at the terms that are in what we're trying to prove, and see if we can use that to create our proof. So we know that a sub n, if we look at our sub letters, this n is the same as what we'll see in the denominator, and that in the numerator it will be one up from that. So it will be the next or consecutive number. So if this was a 5, this should be a 5, and this would be a 6. So if we notice, we see an n sub 1 in there, or an n minus 1. So that means I should be able to use that same idea, that in my denominator, my sub values should match. So I should have f sub n minus 1. And in my numerator, it should just be 1 up from this. So it would be f sub n. Okay, and then if we go to a sub n minus 2, which is again the other a that we see in this proved value or proved equation, we would say that our denominator has the same sub value of n minus 2, and that the numerator should be 1 up from that. So 1 up would just be n minus 1. So let's go ahead and take this information along with our definition of f sub n to see if we can get this. So if we start with a sub n, we have f sub n over f sub n minus 1. Now we have a definition for f sub n here. And in fact, we're going to just substitute that in. So we're going to say that f sub n is equal to f sub n minus 1 plus f sub n minus 2. Remember, this is what we said, that if you want to find the number of rabbits in a particular month, add up the values or the number of rabbits from the 2 previous months. So n minus 1, n minus 2. And we're going to put that over n minus 1. Well, notice something. You have an f sub n minus 1 in your numerator and your denominator. So we could split this up into 2 fractions and rewrite our first fraction as just simply a 1. So let's do that. So we'd have 1 plus f sub n minus 2 over f sub n minus 1. So we're getting pretty close here because we said that this starting off was, we said that this starting off was a sub n minus 1. That's what this equals. So how is it that we can connect this last piece to this idea of 1 divided by a sub n minus 2? Well, look. If you look at a sub n minus 2, it's f sub n minus 1 over f sub n minus 2. And these two are reciprocals of each other. See how they're just flipped upside down? So you could say that this here, this portion, the f sub n minus 2 over f sub n minus 1, is really the same as 1 over a sub n minus 2. And you've proven what we have in the box. I'll bring that a sub n minus 1 down there. So we've proven it. Good. So now our next piece is to consider what it says about finding a limit. That was the next part of part B. It says that if we assume that a sub n is convergent, let's find its limit. So we said that when a value is convergent, that means that the limit of the sequence as your months progress towards infinity, or as your n progresses towards infinity, is L. And it looks like I'm actually going to run out of time in this video, so I'm going to end it right here and create another video looking at how we will prove or find the limit of this convergent set.